welcome to our channel Knowledge Hub. Friends, subscribe to our channel and click the bell icon for the latest update. Today we're gonna start with your chemistry for the class 12th here, and that is your class your 19th, and we had done your 18 classes before. First of all, it's a huge request from my side to all the viewers to please go through with the subscribe button and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. In terms of chemistry here, that is we had started with unit 7 here, that is the P block element, where we had completed your unit 1, unit 2, unit 3, unit 4, unit 5 and unit 6, and we had started with unit 7 in the last classes, and hopefully if it does not succeed exceeded more than hour, so yes, we'll surely complete that, and otherwise we'll complete in the next coming classes as well. Before starting with this, it's a huge request from my side to all the viewers to please go through with the subscribe button and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. On the same case, last we had discussed about which is your about the nitrogen here, and that is your the properties of nitrogen, and in the same case we will discuss about the Lewis dot main resonance, that is the structures of bond parameters of oxide that were discussed here, which is the structures of oxides of nitrogen, and that we have to discuss here. So let's go ahead to make it a sort of a table here. First, this is a structure of oxides of nitrogen that we have to go ahead. So for the formula, we have your formula, then we have your which is the another one is your the resonance structure, and the third column we have here is your bond parameter. So for the formula, we'll discuss the first formula we have to discuss is your N2O. The second formula we'll discuss about NO. The third formula we'll discuss about N2O3. The fourth we'll discuss about NO2, N2O4, N2O5. This we have to discuss here. Okay. Okay, so here we go ahead, and that we even have to discuss about it for each here and in a detail, of course. For the N2O, that we have to represent the resonance structure. For that we have here is like N double bond N double bond oxygen. We have a 2 lone pairs here. This is it is not consisting of lone pair, sorry, this is being consisting of 2 lone pair as well. So with the same case, it will be triple bond N. This is being the lone pair here. Okay, this is what we have, and according to the resonance structure, we have a bond parameters will represent in the form of N bond N bond O. This is your 113 pm. This is of length of 110 pm, and it is linear. Now coming to the NO here, which is double bond O. We have 2 lone pairs with 1 there atom. This is 1 lone pair. Then we have your a double bond O, and this is we have N bond O, which is 115 pm. For N2O3, it is N double bond O. We have bonded N, double bond O with this, and this is O. We have bonded, and here N bond N, O, the bond O, double bond O here. And for the bond parameter we talk about it, so this is N bond N, bond O, here as well O, this is also O, this is 114 pm, and the angle they formed is 105 degrees Celsius as well. So on the same cases for the another one we'll talk about it, and that is we have for that. So here we go ahead for that, and that we have is your NO2, and on the same cases we'll have to form it out. Bond, single bond, that is oxygen here, double bond O. So it will be giving us as that is your double bond O with lone pair 3. Okay, so for the same case, this is what we have, as I had not represented it. This is a 114 and an angle they are forming is 105 here. This is 186 pm, and this is the angle what they are forming is your 117 degree, and this is your 121 pm, and the angle they are forming in between is your 130 degree here. Okay, so this is what, and that the figure will be is your planar. Okay, now we'll talk about the third one here, that we have a category of this, and that even though we have to talk about it. And for that the bond parameters we have as follows, which is to be like N, this is O, and this is O as well. So what they are forming, this is your 120 pm, and the angle what they are forming is your 134 degrees Celsius, and that is 134 degree, and that the figure we have is your angular. Now we'll go ahead with another figure which we have to find out. This is N2O4. So here we have N2 and OS4. So we'll go ahead and bond N. The oxygen we have here is with 3 lone pair with double bond, that we have as your here, that is the double bond oxygen as well. And on the same cases it will be coming for the N2O4 as well. Here it is your oxygen. It is forming N bond N, the oxygen. So here it is forming the angle which is 135 degree. This is the length we have 175 pm, and this is 121 pm as well, and the whole structure is known as planar. Now we'll go ahead for N2O5, and here we have N2, and so we have O5. So this will be like this at this point, and it will be having 3 lone pair, double bond oxygen, that is we have 2 lone pair. This is we have your 2 lone pairs, oxygen 3 lone pair, double bond oxygen 2 lone pair, that we have. And on the same here, for the corresponding towards it, we have oxygen and O. So this is being having a 3 lone pair. This is consisting of 2 lone pair, and this is consisting of 3 lone pair as well, double bond, do lone pair, and that is double bond with do lone pair. And here it is NO that we have, and this is your 1:51 p.m. and this is your the angle what they are forming is 112 degree. This is your 119 p.m. This is also the angle is 134 degree, and the structure is known as planar that we have. Now we'll go ahead with another question that we have to talk about it, which is also an important one, and that is why does NO2 dimerize here? So that is we have to talk about it. Why does NO2 dimerize? And on the same cases, this has been the options we have is NO2 contain odd numbers of valence electron and it behave as a typical odd molecule on dimensions. On dimerization it converted to stable N2O4 molecule with even number of electrons. Now we'll talk about the option, the another question we talk about it, which is what is the covalence of nitrogen in N2O4, sorry N2O5, that you have to find out. We'll talk about the another structure which we have to discuss here, and you can see that another the molecular another nitric acid we talk about it. So that is the another category is nitric acid. In terms of nitric acid, where nitrogen forms oxo acids such as H2N2O2 as well, that is your the hyponitrous acid, HNO2 which is nitrous acid, HNO3 nitric acid, and amongst them HNO3 is the most important, which is nitric acid, and that's the reason why we are going to discuss this one here in detail. According to this, we'll be going ahead further, and as I told you, these all are important here. On the same cases, we'll first talk about the preparation for that, and that is it is a laboratory nitric acid is prepared in heating KNO3 and NaNO3 and concentrated with H2SO4 in a glass retort, and that we have here, which is your NaNO3 plus H2SO4 will give NaHSO4 plus HNO3 here. In the same case, on a large scale, it is prepared mainly by Orthophosphorus process, and that this process is based upon that is your catalytic oxidations of NH3 by atmosphere oxygen. And for the same case, we have a reaction is 4 NH3 gases plus 5 O2 gas in the presence of PT and RH, that is a cold catalyst at 500 Kelvin, 9 bar will give 4 NO form of gas plus 6 H2O here. That is your in the form of gases here. Here it is your from here. This over here is from here. So nitric oxide thus formed and combines with oxygen give NO2, and on the same cases we have 2 NO plus O2 gases form will give 2 NO2 gases here. The nitrogen dioxide so formed dissolves in water to give HNO3, and which is your 3 NO2 in the form of gases plus H2O liquid will give 2 HNO3 aqueous plus NO form of gases here. So no thus formed is recycled, and aqueous HNO3 can be concentrated by distillations upon up to 68% by mass, and further concentration to 98% that can be achieved by the dehydration with the concentrated H2SO4. In terms of properties, if I'm going ahead, so it has been colorless liquid, like freezing point is to 231.4 Kelvin and boiling point is 355.6 Kelvin. While laboratory grade nitric acid contains 68% of HNO3 by mass and has a specific gravity of 1.504 as well. In a gaseous state, HNO3 exists as a planar molecule and hydronium and nitrate ions as well. So on the same cases we have HNO3 aqueous plus H2O liquid will give H3O plus aqueous plus NO3 aqueous here. In the same cases, the formula for that we have here is ONO, and this is H here. This has been 102 degree, 140 here, 0.6 pm. This is 130 degree, this is 121 pm, and this is 96 pm here. On the same cases for the another, that is the concentrated nitric acid is a strong oxidizing agent and attacks most metals except noble metals such as gold and platinum. The product of oxidation that depends upon the concentrations of acid, temperature and the nature of the material undergoing oxidation here. We'll talk about for that. We have equations here for this, like that is we have is your 3 Cu plus 8 HNO3, which is your dilute. We'll give 3 Cu NO3 whole twice plus 2 NO and plus 4 H2O. The another we have here, that is Cu plus 4 HNO3 concentrated. We'll give Cu NO3 whole twice plus 2 NO2 plus 2 H2O that we have. So zinc react with dilute nitric acid to give N2 with the concentration acid to give NO2 here, and for that same case we have here 4 Zn plus 10 HNO3 dilute will give 4 Zn NO3 whole twice plus 5 H2O plus N2O as well. The another we have here Zn plus 4 HNO3 concentrated will give Zn NO3 whole twice plus 2 H2O plus 2 NO2 that we have. On the same cases here, some metals, example like chromium and aluminium, that do not dissolve in the concentrated nitric acid because of the formations of a passive film of oxide of the surface, and concentrated nitric acid also oxidizes non-metal and their compound, and iodine is oxidized to the iodic acid, and then the carbon to the carbon dioxide, sulfur to H2SO4, and the phosphorus to, of course, the phosphoric acid as well. So here we go ahead further, and that we have your another equations we'll talk about it, which is also an important one. So just I will go ahead here and to be the detailed be writing it out as well. So they are making you know, in a 4 different equations that we have to form it out. It's just I2 plus 10 HNO3 will give 2 HiO3 plus 10 NO2 plus 4 H2O. Another is C plus 4 HNO3 will give CO3 plus 2 H2O plus 4 NO2. Another we have S of 8 plus 48 HNO3 will give 8 H2SO4 plus 48 NO2 plus we have your 16 H2O here, that we have your answer as well. On the same cases we have the another one for that is your P4, and which is P4. We have P4 plus 20 HNO3. It will give you 4 H3PO6 PO4 plus 20 NO2 plus 4 H2O here, that we have as the equation here. From that, Brown's ring test, that the familiar Brown ring test for the nitrates, that depends on the ability of Fe2 plus to reduce the nitrate to the nitric oxide, and which react with Fe2 plus to form a brown colored complex. The test is usually carried out by adding a dilute ferrous sulfate solution to the aqueous solution that containing the nitrate ion, and then carefully adding the concentrated sulfuric acid along the side of the test tube, where a brown ring at the interface between the solution and the sulfuric acid, that layer indicates the presence of nitric ions in the solution as well. So for that, it will be forming in the form that we have your equations here, that we have to represent by NO3 here, that we have as follows. So for the same, we have here the equation that we have to represent it as well, and this we have as follows, like NO to 3 plus 3Fe2 plus 4H plus, that will give NO plus 3Fe2 plus 3 plus plus 2H2O, and for the same case it is your FeH2O 6 plus 2 plus NO will give FeH2O 5 NO 2 plus H2O. This is in brown in color. Okay, now we'll go ahead for the uses here. In the same cases for the coming towards, that is your uses here. In terms of uses, the major use of nitric acid is in the manufacture of ammonium nitrate, for fertilizers and other nitrates, for the use of the explosive and pyrotechnics, that it is also used for the preparations of nitroglycerin and trinitrotoluene and the other organic nitro compounds. Other major uses are the pickling of stainless steel and etching of metals, and as the oxidizers in the rocket fuels as well. Other than that, if I'm going ahead to be discussed, which is the another element we have to discuss is the phosphorus, which is allotropic forms. We'll have to go ahead and that will discuss here in the detail about it, because these all are important as a respective manner, in a respective manner, we can say that. And on the same conclusion, we have to go ahead, and that is which is also important here. So we'll go ahead for the phosphorus here, that is the phosphorus allotropic forms. So in the same cases here, where phosphorus is found in many allotropic forms, and the important one being white, red and black. White phosphorus is translucent, white or waxy solid, and it is a poisonous, insoluble in water, but soluble in carbon that is disulfide, and that glows in dark, which is your the chemiluminescences, and it dissolves in boiling NaOH solution in an inert atmosphere, that is giving pH 3 as well. And for the same cases, the reaction for this we have is your P4 3 NaOH, P4 plus 3 NaOH plus 3 H2O will give pH3. This is your phosphine plus 3 NaH2 PO2, which is sodium hypophosphite. Sodium hypophosphite. Okay, that we have to talk about it. And white phosphorus is less stable and therefore the more reactive than the other solid phase under the normal condition, because of the angular strains in the P4 molecule, where the angle are only 60 degree, and its reactivity catches the fire in air to give the dense white fumes, which of P4HO10 as well. On the same cases, it is the reaction we have here, which is P4 plus 5O2, it will give you P4O10 here. On the same cases, for the references we have, which is P here, all, and that is connected to one another with a bond here as well, and this is making the angle which is 60 degree here. Here it consists of discrete tetrahedral P4 molecule that we had represented here, where the red phosphorus is obtained by heating a white phosphorus at 573 Kelvin in an inert atmosphere for several days. When red phosphorus is heated under high pressure, a series of phases of black phenomena is formed, and the red phosphorus possesses iron-gray luster. It is colorless, non-poisonous, and insoluble in water as well as in a carbon disulfide. Chemically, the red phosphorus is much less reactive than the white phosphorus, and it does not glow in the dark here. On the same cases for the same here that we have to go ahead, and which is on the same cases we have to go ahead, and that is also an important one here, and with the same references towards it, and that we have to discuss here in the detail as well. So on the same here, that is we'll discuss about the red phosphorus as well in the detailed here, and that is in the same cases. It is of course that is your polymeric that is consisting of the change of p tetrahedra linked, and that is together in the manner that we will be discussing here. So that is we'll discuss with the different pens, so that it will be let you enable in a different way. So on the same cases, that has been your the red phosphorus being connected towards like this. This is P. Okay, so P, P, P. This is like as such that I had represented above here, but they are connected towards many. This is your red phosphorus. Then we have your connected to it. This is known as red phosphorus. In some same cases for that, the black phosphorus has two forms, which is your alpha black phosphorus and a beta black phosphorus. And alpha black phosphorus is formed when the red phosphorus heated in a scaled tube at 803 Kelvin, and it can be sublimed in air and has an opaque monoclinic or that is rhomboidal crystal. It does not oxidize in air, and a B black phosphorus is prepared and heating white phosphorus at 473 Kelvin under a high pressure. It does not burn in air up to 673 Kelvin as well. Now we'll talk about another one, which is the phosphine here in that same cases. The phosphine for that will go ahead, which is your phosphine. In terms of phosphine, this is for the preparation of that the phosphine is prepared by the reactions of calcium phosphide and of course that is the water or dilute HCl as well. So we'll discuss the phosphine with dilute HCl as well as for the water as well, that the reaction what it will make here. On the same cases, the reaction we have here is to be as follows, which is your Ca3P2 plus 6H2O, that will give 3 CaOH twice plus 2PH3. Another equation is your Ca3P2 plus 6HCl, that will give you 3 CaCl2 plus 2PH3 here. In the laboratory, it is prepared by heating white phosphorus with concentrated NaOH solution in an inert atmosphere of CO2. For that, we have your P4 plus 3 NaOH plus 3H2O. It will give PH3 plus 3 NaH2PO2, which is sodium hypophosphite, as I told you about here only. Okay, for the same cases here, and when a pure, it is not inflammable. When it is pure, then it is not inflammable but becomes inflammable, when you are owing to the presence of P2H4 or P4 vapors, that to purify it from the impurities, and it is absorbed by NHI to form the phosphor, that is your phosphonium iodide, PH4I, which treated with a KOH, that gives off phosphine as well. And for the same case, we have an equation here, PH4I plus KOH, it will give Ki plus H2O plus pH3 as well. For the properties we talk about it, it can be colorless gas with a rotting fish smell and is highly poisonous, and it explodes in contact with the traces of oxidizing agent like HNO3 and Cl2, and of course Br2 vapors as well. On the same cases, with reference towards it, we'll have to go ahead, and as I told you, it is a slightly soluble in water, and the solution of pH3 of water that decomposes in the presence of light giving red phosphorus and H2N when absorbed in the copper sulfate and mercuric chloride solution, where that the corresponding phosphorides are obtained here, and the reaction that we have formed is your 3CuSO4 plus 2pH3 will give Cu3p 2 plus 3H2SO4, where 3HgCl 2 plus 2pH3 will give Hg3p2 plus 6HCl here. And the phosphine is weakly basic and like ammonia that gives the phonium compounds with acid. Like example we have is your pH3 plus HBr will give pH4Br here, that we have to talk about it. On the same cases for them, we'll have to talk about the uses here, that is also an important one. Then the terms of uses, that the spontaneous combustion of phosphine is technically used in the Holmes signals and containers that containing the calcium carbide and calcium phosphide that are fired and that thrown and in the sea when the gas is evolved, burned and severed that as a signal, and it is also used in the smoke screens as well. Now we'll go ahead with the question that we have to solve it out in terms of it, and which is the question is, in what ways that can be proved that pH3 is a basic in nature, and that you have to solve it out. So for the same cases, we will be going ahead here in the detail about it. So the question which is that we have to react with it, and we have to even give us answer as well. So let's go ahead for that as well. So the first we'll have a question here. The question is, in what way can it be proved that pH3 is basic in nature? That we have to go ahead. So here pH3 reacts with acids like HI, and that to HI to form a pH3I, which shows that it is a basic in nature here. On the same cases, that has been reacting like this, pH3 plus HI, which will give pH4I. Due to the lone pair on a phosphorus atom, pH3 is acting as Lewis base in the above is this reaction here. Okay, now we have another questions in terms of it, like what is you have to explain that bond angle in pH3 is higher than the pH3 here. So pH4 plus is higher than in pH3, that you have to answer it out. Why? With an detailed example. And the other question is your, what happens when a white phosphorus is heated with a concentrated NaOH solution in an inert atmosphere of CO2? So that you have to find out, and if you not get it out, it is an answer, so you can just tell me on a comment section. I will be provided you that soon as well. So okay, but the point is that you have to, first of all, you have to do by your own side, and if you're not getting after many practice, then I will surely provide you that. Let's go ahead with another one which we have to discuss here, which is your, in terms of this is phosphorus halides. In terms of phosphorus halides, we have to talk about it. Phosphorus halides here, that is the phosphorus forms the two types of halide, which is px3, where x can be your fluorine, chlorine, bromine, iodine, and px5, which is x also can be your that is fluorine, chlorine, or bromine. So first we'll discuss about the phosphorus trichloride, then phosphorus pentachloride as well. So all the halides that we have to even discuss about it. So the first we'll discuss here is about your the phosphorus trichloride. In terms of phosphorus trichloride, we are talking about the preparations here. It is obtained by passing a dry chlorine over heated white phosphorus, which is the reaction for that we have here is that it is also been, I just write it down here. It has also been like P4 plus 6Cl2 that will give 4 PCl3. It is also obtained by the reaction the thionyl chloride with the white phosphorus. For that P4 plus 8SOCl2 will give 4 PCl3 plus 4SO2 plus 2S2Cl2 here. For the preparation, it is a colorless oily liquid and hydrolysis in the presence of moisture. So for the same we have PCl3 plus 3H2O. It will give H3PO3 plus 3HCl as well. This is H3PO3 is your phosphorus acid here, and it reacts with an organic compound that containing the OH group such as CH3COOH or C2H5OH. So on the same case we have a structure for this, that is PCl, Cl, and this is your Cl, and this is your having a lone pair. Okay, this is about it. And for the same cases we have a reaction for this as well. 3CH3COO. Okay, it is not seen. Okay, CH3COOH plus PCl3, it will give 3CH3COCl plus H3PO3, and the equation is 3C2H5OH plus PCl3, it will give 3C2H5Cl plus H3PO3 here. It has a pyramidal shape as shown, in which the phosphorus is sp3 hybrid, that is hybridized here. Now we'll go ahead with another one which we'll talk about it, which is the another one here, and on the same cases, which is phosphorus pentachloride, that we have to talk about it, and even though which is also an important one here, and that is also, we'll have to go ahead. So that is the phosphorus pentachloride, we talk about it here on the same case. So phosphorus pentachloride, we talk about it. In terms of phosphorus pentachloride, that is also an important one, and in the same cases here, for the preparation, that the phosphorus pentachloride is prepared by the reaction of white phosphorus with the access of dry chlorine as well. On the same cases, we will be going ahead here in the detail about it, which we have. So on to the same cases, we have the equation for the pentachloride that we have is your P4. I'll write it down with a different pen. P4 plus 10Cl2, it will give 4PCl3 here, sorry, PCl5, okay, 2 here that we have here, which is your 5 here. And it can be prepared by the actions of SO2Cl2 on phosphorus, which is P4 plus 10 SO2Cl2 will give 4 PCl5 plus 10 SO2 here. On that same case, we have a preparation for that, and PCl5 is a yellowish white powder, and as most in moist air, it hydrolyzes to the POCl3, and that finally get converted to the phosphoric acid as well. So for the same case we have here, which is PCl5 plus H2O will give POCl3 plus 2HCl, and for the same here, that is POCl3 plus 3H2O, it will give H3PO4 plus 3HCl here, that we have as here, that will be the right answer. And on the same cases, we'll go ahead further, which we'll talk about it as I told you. So on the same for that when you know that heated, it is sublimized and decomposes on a stronger heating. So on the same case for that, we have PCl5 is on heated, then we'll get PCl3, it is break it out, and plus Cl2 as well. So it reacts with an organic compound containing OH groups at conversions, and then to the chloro derivatives as well. And on that same case, which we have C2H5OH plus PCl5 will give C2H5Cl plus POCl3 plus HCl. Here CH3COOH plus PCl5 will give CH3COCl plus POCl3 plus HCl here. Finally, divided metals on heating with PCl5 that gives corresponding chlorine, and on that same case we have a reaction that is 2Ag plus PCl5 plus, that tends to AgCl plus PCl3 here, and which is to be as follows. And then another equation we have Sn plus 2PCl5 will give SnCl4 plus 2PCl3 here. And the same here for the reactions we have here, and that is to be as follows is your PCl, this is Cl, this is Cl, this is Cl, this is Cl, we have 5Cl as well. So this is your dotted line they had attached towards it. And on the same cases, this is Cl is your 240 pm, this is 202 pm, these all, and that is the PCl5 have been structured here. On the same cases, it is used in the synthesis of some organic compound with example C2H5Cl, CH3COCl. In a gaseous and a liquid phase, it has a trigonal but bipyramidal structure as shown, and that the 3 equatorial PCl5 bonds are equivalent, and while the 2 axial bonds are longer than equatorial bond, and this is due to the fact that the axial bonds pair suffers more repulsions as compared to the equatorial bond pairs as well. In the solid state, it exists as an ionic solid, which is PCl4, PCl6, in which the cation PCl4 is a tetrahedral, and anion PCl6 is your octahedral as well. Now we'll go ahead with another question that we have to talk about it in terms of this topic only. The question we have here, which is to be as follows, and that is also important one. So that the question is, why does PCl3 fume in moisture? Why does PCl3 fume in moisture? So in this here, that is PCl3 hydrolysis in the presence of moistures giving the fumes of HCl, and that is when we have an equation here for that, which is your to be as follows, like PCl3 plus 3H2O, it will give H3PO3 plus 3CHCl. Another question that we have even though have to discuss about it, which is also an important one here. On the same cases, the question is we have that is your the question is your are all the 5 bonds in PCl5 molecules equivalent? Justify your answer. So let's go ahead with question, then we'll talk about it. Are all the 5 bonds in PCl5 molecule equivalent? In the same cases for that, here that the PCl5 that has trigonal bipyramidal structures, and the 3 equations the like PCl bonds are equivalent, and while the 2 axial bonds are different and longer than the equatorial bonds as well. We'll go ahead with another question that we have to talk about it, that is as a homework for you all. What happens when PCl5 is heated? And the other is write a balanced equation for the hydrolytic reactions of PCl5 in a heavy water here, that we have to go ahead with the discussion about it. Now we'll discuss about the oxo acids of phosphorus, which is also an important one, and we will talk about H3PO3 and as well as many more H3P2O7 and all related things. And then after that we'll complete that group of 15 elements, and surely we'll start discussing about your group 16 element in that, even if it is not longer, then we'll continue in this next class only, otherwise we'll exit it for the next class here. Let's go ahead with this. So here we go ahead, and as I told you that we have to discuss about it, which is about your oxo acids of phosphorus. Oxo acids of phosphorus that we have to talk about it, where the phosphorus forms the numbers of oxo acid and the important oxo acid phosphorus with their formulas, that method of preparations and presence of some characteristics bond in their structures. We will talk about where we have to discuss about that is the oxo acids of phosphorus here. So we'll talk about the name, and then after that we'll talk about formula, oxidation state of phosphorus, characteristics, bonds and their numbers, and of course the preparation as well. So we'll go ahead here. So first we'll discuss about that is your name. The another we have is the formula. Then we have oxidation state of phosphorus. The another we have characteristics, bonds and their number. Then we have your preparations. Okay, so for then on the same cases we'll go ahead. The first name we have here is that we have to discuss about it, which is your the hypophosphorus, which is your phosphinic. Okay, the name is your hypophosphorus, and the nickname you can say that we call about it is your phosphinic. Okay. Okay, so this has been the formula been shifted here. So the next for that same case, the formula for this we have as follows. Under the same cases we have to go ahead, and that is for the formula we have here that we have to represent it as well, and even though this we have to discuss here as well. The formula for that is your which is H3PO2. On the oxidation state of phosphorus we have your +1. The characteristics, bonds and their numbers we have here. If it is 1p bond OH, 2p bond H, and 1p double bond O here. And where in the preparations we are here you have is white P4 plus alkali. Okay, now the second we'll talk about it, which is the orthophosphorus, or it will be known as your phosphonic. So that we have as follows: Orthophosphorus, which is also known as phosphonic. Okay, so for the same case we have here, just I will draw a line here where you will get to know. Okay, so now it is, I think that is very clear. The formula for this we have is your H3PO3. Then we have your that is oxidation state of phosphorus is +3. So for that it is 2P OH 1 PH 1 PO here. That is being double bonded. Okay. On the same cases we have here, that is your P2O3 plus H2O that we have. The another we talk about it, which is your being as pyrophosphorus. We'll talk about the different band. In same cases for the pyrophosphorus, the formula we have is your H4P2O5 plus 4. For the same cases, 4POH 2 P double bond O and 1 P bond P here. So here in the same case, which is your red, P4 plus alkali. Now we will be going ahead with another one that we have to discuss here, and which is your hypophosphoric. With hypophosphoric here, which is H4P2O6. That is we have, and on the same case it is your plus okay, this is your +3, sorry, this is +4. So for that same cases it is your 4 P bond OH 2 P double bond O 1 P bond P. On here that is your, it will be your okay, this is as same, so this is not that, which 2P bond 2P bond here, that is your OH, and 2P bond O here, P bond H, single bond H, and one and we have is your 2 only, and that is your 2P double bond O. Okay, and for that it is not red one, this is your PCl3 plus H3PO3, sorry for that, red P4 plus alkali. Okay, that we have to talk about it. Now we will be going ahead further, we will discuss about it, that is another one here, and which is your orthophosphoric here, which is also important. So on the same case for the orthophosphoric, so the another we have here, orthophosphoric. So in orthophosphoric here, the formula we have is your H3PO4, which we have, and this is +5. So on the same cases here we talk about it, which is 3 P bond OH and 1 P double bond O. So this is P4O10 plus H2O. Now we'll go ahead with another one that we have to discuss is your pyrophosphoric. Pyrophosphoric. So for the same case we have here is your H4P2O7. This is plus 5. Here 4 P bond OH, 2 P double bond O, 1 P bond O, 1 P. Here that is your heat phosphoric acid. Phosphoric acid. Okay, so in the same cases we have the another one, and the last one that we have to discuss here for that the name here that we'll discuss is your metaphosphoric here. So that we have is your metaphosphoric. The formula for this we have is HPO3N. This is plus 5. So here on the same case is 3P, 3 P bond O, H, 3 P double bond O, 3 P bond O bond P. Then for that phosphorus acid plus Br2, where heat is heat in a sealed tube. Heat in a sealed tube, that we have to talk about it. So here that exists in the polymeric, and the characteristics that we have to discuss as well, which is also an important one, and that we have to complete it out. Okay, on the same cases here that the concentrations of the oxo acids are interrelated in terms of loss or gain of H2O molecules or O atom as well, where the structures of some important oxo acids cytopy are given below: H3PO4, H4P2O7, H3PO3 and H2PO2, and then we'll discuss about HPO3, which is metaphosphoric acid, and that is your polymetaphosphoric acid, which is HPO3. And here that even though we had discussed the structures for those as well, so that is also an important one. But on the other hand, we'll go ahead here to discuss. So we'll discuss the structures first. Okay, which is P double bond O bond OH OH OH. So that is the formula we have is H3PO4, and the name of that is your Orthophosphoric acid. Okay, now I'll talk about the another one which we have is your P bond O bond P, double bond O, double bond O, single bond OH OH, and that is your P bond OH bond OH here. This is the formula we have here. You have H4P2O7, and that is name is your pyrophosphoric acid. The another we talk about it, which is the another one here, is your P double bond O bond OH bond OH and bond OH. So it's only H. And then we have here the formula for this we have is H3PO3, and the name is Orthophosphorus, which is orthophosphoric acid. The another structure we have is your P double bond O bond H bond H bond OH. This is your H3PO2. The name is hypophosphorus acid. The another we talk about it, which is another one, is your P bond O bond P double bond O, pair double bond O. This is O P O P double bond O bond OH. This is bond H as well. This is your OH here. Okay, so this is what the structure we have, and on the same basis for this particular structure, that we have as follows. This is bond OH as well here as well. That is, this is your the cyclo or tri-metaphosphoric acid, which is cyclo tri-metaphosphoric acid, and the formula for this we have is your HPO3 whole N here, that we have, that we will take as 3, so that is been representing the 3 here. Okay, now we have a one more left, and that is your polymetaphosphoric acid, which is HPA3N here. That is also the large one here that we have to discuss. So here we'll be ending it up, and we'll discuss that in the next coming classes. That is also important one. So on the same behalf of it, it's a huge request from my side to all the viewers to please go through with the subscribe button, and please like, share and subscribe our channel, so that many maximum people can get the information at once, and even though you can also enjoy the video as well. Other than chemistry, if I'm doing a other than chemistry, we are dealing with quantitative aptitude, where we had started with arithmetical ability, where we had completed your operations on numbers, LCM and SCF of numbers, decimal fraction, and we had done your operations on numbers, and then we had done simplification of square roots and cube roots and averages we had completed. In the next coming class, we will start discussing about the next new topic of averages of the the data sufficiency part. After that, talking about the reasoning here, so that we had completed your verbal reasoning, and where we had completed in that we had completed general mental ability in the logic reasoning. Other than that, we had completed your non-verbal reasoning, where we had completed series, analogy, classification, analytical reasoning, mirror image, water image, embedded figure, completion of incomplete pattern, and your figure matrix. And then we have to cover up other more than that as well, and that is the another new topics as well that we have to discuss here. Other than that, we had completed your sociology and software engineering. In terms of chemistry, if I'm going ahead here, we had discussed about unit 1, which is your solid state, and we had completed general characteristics of solid state, amorphous and crystalline solid, classification of crystalline solid, crystal lattice and unit cell, number of atoms in unit cell, closed pack structure, packing efficiency, calculation involving unit cell dimensions, imperfections in solid, electrical properties, magnetic properties as well. The unit 2 is your solution, that we had completed your types of solution, expressing the concentration of solution, solubility, vapor pressure of solid liquid solution, ideal and non-ideal solution, colligative property of the determination of molar masses, abnormal molar masses as well. In unit 3, which is your electrochemistry, electrochemical cells, galvanic cells, Lorentz equation, conductance of electrolytic solution, electrolytic cells and electrolysis, batteries, and then after that we talk about it, so that we had completed the fuel cells and corrosion as well. In unit 4, we had completed your chemical kinetics, rate of chemical equation, pattern influencing the rate equation, integration rate equation, pseudo first order reaction, temperature dependence and the rate of the reaction, collision theory of the chemical reaction as well. In the 5th page, we had completed your surface chemistry, adsorption, catalyst, colloids, classification of colloids, emerging colloids around us. Unit 6 is general principles and process of isolations of element, where we had completed occurrence of metal, concentration of ores, extractions of fluid metals and from the concentrated ore. Then after that, we had completed the thermodynamic principles of metallurgy, electrochemical principles of metallurgy, oxidation, reduction, defining uses of aluminium, copper, zinc and iron as well. Another is the unit 7, which we had completed the P block element, where we had completed group 15 element, dinitrogen, ammonia, oxides of nitrogen, nitric acid, phosphorus, allotropic, phosphine, phosphorus halide, also acids of phosphorus, group 16 element, acids of phosphorus we had started, and even though we had completed the 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 one figure which we have to complete it by the end that we have to complete it. So after that, completing with that, we will start discussing about group 16 element. Here we have to complete dioxygen, simple oxides, ozone, sulfuric, sulfur, allotropic form, sulfur dioxide, and then after that oxo acids of sulfur, sulfuric acid. After completing that, we'll have to start discussing about group 17 element, that is your chlorine and hydrogen chloride, oxo acids of halogens, interhalogens compound, group 18 element. Then we'll discuss that. After that, we'll have to start discussing about unit 8, which is the D and F block element, which is we have to complete the positions in the periodic table, electronic configuration of the D block element, general properties of the transition element of the D block, some important compounds and the transition element, the lanthanides, actinides, some applications of the D and F block element as well. Where we have to complete the coordination compound, that is your unit 9, which is we have to discuss about the oneness theory of the coordination compound, definitions of some important terms pertaining to the coordination compound, nomenclatures of coordination compound, isomerism of the coordination compound, bonding in coordination compound, bonding in methyl carbonates, stability of the coordination compound, importance and application of coordination compound as well. So here we'll be ending it up, and first of all, it's a huge request from my side to all the viewers to please go through with the subscribe button and please like, share and subscribe to our channel so that many and maximum people can get the information at once and you can also enjoy the video as well. Thank you. Hope you enjoyed this video. If you like this video, please give a thumbs up and give a suggestion on a comment box. Thank you.